Hello, welcome to Basics of Finite Element Analysis MOOC course. Today is the 5th day of the current week, and our theme for the discussion today will continue to be the same which we were doing in the last class. That is the notion of Jacobian and how it influences and the role it has in computation of integrals of functions over an element domain. So, we had shown in the last class that the derivative of x, at least in one dimensional system, with respect to zeta is known as Jacobian of the x to z or zeta transformation, and it can be explicitly calculated using this relation, and it is symbolized in this course as J subscript E. So, dx can be written as Je times d zeta, and then if I am interested in finding out the integral of fx over the domain xa to xb, then in the natural coordinate system it can be expressed in this form. So, this is the form which we will use when we will actually do the numerical integration using Gaussian quadrature scheme. Now, we still are not there at Gaussian quadrature, but we are getting close to that. And but before we discuss any new topic, I will like to explain you this Jacobian by an example. So, we know that Je equals summation xi, so these are constant, xi's are constants, times derivative of psi I for the eth element with respect to zeta, and here I ranges from 1 to m, and m minus 1 is order of polynomial. That is the order of polynomial. Now, we will do an example. Let us say m equals 2, which means that the approximation of geometry is of what type? It will be of linear type. If m is equal to 2, then approximation of geometry will be of linear type. So, the first approximation function psi 1 will be half of 1 minus zeta, and how did we get this? We got this relation essentially by following or using this equation C, which we had developed a couple of lectures earlier. This is the first approximation function, psi 1 equals half of 1 minus zeta, and then psi 2 equals half of 1 plus zeta. Okay. So, then d psi 1 by d zeta equals minus 1 by 2, and d psi 2 over d zeta equals 1 by 2. So, for this transformation, a two noded element xa to xb is being transformed into a two noded element in zeta domain minus 1 to 1. So, this is my zeta coordinate, this is my x coordinate. I am transforming it from here to here, right. So, I have to compute the Jacobian of transformation, that is our aim. So, our aim is what is Jacobian. Okay. So, the relationship for Jacobian is summation of xi d psi I over d zeta. So, and what is x1? x1 is x A and x 2 is x B, right. So the Jacobian for each element is this expression, and if I expand it, it will be x 1 E d psi 1 over d zeta plus x 2 E d psi 2 over d zeta, and of course I have to put superscripts. So this is equal to x A times minus 1 by 2 plus x B times 1 by 2. So this is equal to x B minus x A over 2, and that is equal to h E over 2. This is h E, element length. So in this case, the Jacobian is nothing but half the element length of the original element in x domain. You can try the same thing for m is equal to 3 also. So in that case, psi 1 E will be half of zeta minus zeta 2, zeta minus zeta 3, psi 2 is equal to minus zeta minus zeta 1, zeta minus zeta 3, and psi 3 is equal to half of zeta minus zeta 1 and zeta minus zeta 2. Now you can again compute d psi 1 over d zeta, d psi 2 over d zeta, d psi 3 over d zeta, and then what is x1 in this case? x1 equals xa, x2. So x1 equals xa for m is equal to 3. What does m is equal to 3 look like? I have a 3 noded element, node 1, node 2, node 3, and this is xa, xb, and this midpoint is xa plus xb by 2, and this I am transforming to zeta coordinate system. So it is minus 1, 0, 1, and nodes are 1, 2, and 3. Okay. So here I am calculating the Jacobian for this transformation. So Jacobian is specific to the order. Okay. So you do all these calculations. So what you will find is that Jacobian in this case is equal to x1 E d psi 1 over d zeta plus x2 E d. So excuse me, before I write this relation, x1 is xa, x2 is xa plus xb over 2, and x3 is xb, right. So now I using this, I write down the relation for Jacobian. The Jacobian is Je equals x1 d psi 1 over d zeta plus x2 d psi 2 over d zeta plus x3 d psi 3 over d zeta, and these d psi 1 over d we can calculate, we can do differentiation and we can do that. So if we plug all this in here, we will find that even for m is equal to 3, Jacobian is He over 2. I will make a very important observation for all straight line elements, Je is equal to He over 2 regardless of m, regardless of m. But if there are curved elements involved, then J is changing. It changes it depends on the value of m. But for all straight elements, J is equal to He over m, He over 2. Okay, this is important to note. And you can verify this statement by doing this calculation, and you can do it for m is equal to 4, 5, whatever. You will always end up with Jacobian of this transformation as half of the length of the element. This is another concept and another observation which is worth remembering. The next concept I wanted to talk about is types of formulation. Types of formulation. So we had said that in FEA we do two types of approximation. One is the approximation for the variable, right. So we had for instance, if the variable is u as a function of x, then we can express it as j is equal to 1 to n uj e psi j e x. Okay. This is approximation of the unknown variable. For if there is a bar problem, then u is the unknown variable, and uj's are the values of u, they are constants, and their values of u at the nodes of the element. And then the other approximation is of geometry. So x, we have said that it is xi psi I, which is a function of zeta, I is equal to 1 to m. Okay. So let us make it a little more clear. So here summation is happening till n, and here summation is happening till m. So here order of approximation function is equal to n minus 1, and for geometric approximation order of approximation function, and these functions are also known as shape functions for x to zeta transform, they are also known as shape functions. The order of approximation function is m minus 1, right. If here m is equal to 2, then it will be a linear transformation. If m is equal to 3, it will be quadratic transformation. So like this. So there is one order of approximation function for unknown variables, and then another order for geometric approximation where the transformation from x to zeta is involved. Okay. So these are two different things, and we should not get confused. Okay. We should not get confused. So that is why they are very clearly spelled out here. But there is no rule that they have to be always different. Okay. So we can do FEA in three scenarios. So first one is if m is less than n, okay. If m is less than n, then the FEA formulation is called subparametric formulation. Subparametric formulation. Example: earlier in part 1 we had developed Euler-Bernoulli beams. We had developed a method for doing FEA for Euler-Bernoulli beams. There the approximation, what was the unknown variable there? The deflection of the beam, which is W. W was the unknown variable, right, and it is a function of x. There W was nothing but Wj psi j Ex, and these were cubic Hermite polynomials. So W was a cubic function. In W we had psi j's which were cubic functions. Please go and check that. They were cubic functions, right? But x to zeta transformation, you can still have linear transformation or quadratic. So if you do this, then in this case n is equal to what? 4. N is equal to 4, and here m is equal to 2. So m is less than n. So this is subparametric formulation. Subparametric formulation. So the x to zeta transformation can still be linear, but the variation of W over x can be a cubic function. It was actually a requirement of that FEA formulation that it had to be cubic function. So it could, so here n was 4 and m was 2, and in such a case m is less than n, so it is a subparametric formulation. The second case is m is equal to n. M is equal to n. Here this is called isoparametric. A lot of FEA is of this type, isoparametric formulation. For instance, if I am trying to solve this bar problem, I can say that U can be linear, right, over an element. I can say that U can be linearly varying over an element, and in this case n is equal to 2, and at the same time I can say that x to zeta transformation is linear. So m is equal to 2. This is one scenario. Other scenario could be that U is quadratic over element. I can assume that. Then n is equal to 3, and I can consciously choose x to zeta transformation as a quadratic transformation. There is nothing which stops me. Then m is equal to 3. So if this is the situation, then it is again isoparametric formulation, and so on and so forth. So this is isoparametric formulation. And then the last one is m is more than n. This is superparametric formulation. This is not used much. This is not used much, superparametric formulation. So we can have the FEA formulation and the equations developed in different ways. I can have a subparametric formulation where m, which is the approximation order for, which tells us about the approximation order for the coordinate transformation. M is about coordinate transformation. that is less compared to the degree for unknown variables. If both of these parameters are same, then it is isoparametric, and if m is more than n, then it is superparametric formulation. Now, one thing I wanted to mention in this context is that this subparametric formulation, at least in case of this Euler-Bernoulli beam, why did we do that? See, I can have this x to zeta transformation as linear, right, because you have a straight element, you can map it to a straight element, no problem. But we know that W, it varies in a very complicated way in beam. W, it varies in a complicated way in a beam. So, that is why we chose cubic Hermite polynomial. So, the requirement from mathematics side was that we have to go for cubic functions for W, because we have to make sure that for the beam there are two boundary conditions at each edge, right. One is W and also about slope, right, and associated with these boundary conditions at each location or each end could be W is associated with force times W will be work, and slope will be associated with moment. So, anyway, so the variation of, so that is about subparametric formulation. So, these are the three different types of formulation, and at this stage we can start discussing about numerical integration. Numerical integration. So, now with all this background, we will revisit our original problem. Our original problem is that we are interested in integrating this function f(x) dx over the limits xa to xb, okay. And we are not interested in integrating exactly, because we do not know exact nature of f(x), so we cannot exactly integrate it. So, then we say, okay, if we get an approximate integral, we will be happy. So, we integrate it between the limits xa to xb, and because it is approximate, so we choose a slightly different function px, right. What does this mean? So, this is f(x), this is x, this is my f(x), okay. I can say that I do not know how it is exactly varying, but if, so these are the limits for the element xa to xb, I can say that I will approximate the variation between a and b by a straight line. So, this is one option for P1x, it is a straight variation, right, linear variation. So, I will get an approximate integral, the exact integral will be under the purple line, approximate integral will be under the red line. I can make another approximation like this is another approximation. Here I am assuming that it is varying quadratically, right. So, I am in finite element analysis, I am interested in this side of the integral, because I know that I cannot achieve exact integral. So, I am interested in finding the integral either under the red line or the green line, and while I am doing this, I realize that this is important to note that first the function p1 x or p2 x may not be close enough to f of x on a point to point basis. See, on a point to point basis, this red line and purple line, they may not be close. They are having same points at couple of places, but at other points there is a significant variation. But the overall integral may be close because positive errors may cancel out negative errors. You understand this? Positive errors may cancel out negative errors. Let us look at this. Let us look at this. So, consider this green curve. Here we have, this is negative error, and this is positive error. The green curve by itself may not be fairly close to the purple curve. It is definitely not close here at some several locations. But we are not interested in that curve, we are interested in the integral, because that is what we are trying to compute when I am trying to create K matrix or F matrix and things like that. So, I am interested in the integral, and what I see that even if it is an approximate function, this error, this is you can call it negative error, and this is positive error, they somehow cancel out and the integral may be reasonably close. So, maybe this P2 will work for me or even P1 may work for me. This is one. Second is, if element size is small enough, then errors become small as well. Errors become small as well, right. So, if xb was not this far, but xb was, let us say, here, if this was the xb, then I could have just taken a linear line and this would have been much more accurate, or if I had taken a quadratic line, it would have been even more accurate, right. So, 2 points are that there may be positive errors and negative errors, and an approximation function may still be good, and if I make my element size small, then this approximation becomes even better. So, because of both these reasons, reason 1 and reason 2, when we are doing numerical integration, we are focused on finding these approximate integrals, and we say that if we keep on refining the element size to smaller and smaller numbers, this value will be fairly close to fx dx integral, and we will be happy with that approximation. So, this is the overall theme. So, in the next class, we will now start discussing Gaussian quadrature method of numerical integration. So, thank you very much, and we will meet tomorrow.